In this example, the frame supports the 50 kilogram cylinder is given, and we are looking for the horizontal and vertical components of reactions at A and the force at C. So the reason why we're only looking for the force at C, not the components at C, is because this member BC is a two-force member. Again, recall that the very first step that we're going to analyze a frame and machine problem is to identify the two-force member so it can simplify the analysis. Another thing we need to pay attention to is we have a new component in this frame, which is a pulley at point D. So for pulley, usually we're going to take it apart. We're going to analyze the pulley separately. So to analyze pulley, it's a 2D rigid body, but it doesn't have three independent equilibrium equations because the moment equilibrium is automatically satisfied for pulley. So there are only two independent equilibrium equations for pulley, which is sum of fx equal to 0 and sum of the fy equals to 0. Let's first do a quick analysis to see if we have enough information to solve the reactions at point A and the force at C. And first, as we mentioned earlier, this member BC is a two-force member, so I'm going to circle it out to tell myself this is the two-force member. So the force exerted on this beam is along the direction of the beam. And also the reaction, the force exerted on the connecting beam, which is the beam AD, also will be along the direction of this member BC. So that kind of gave me the idea that I will separate the member AD and BC. So the main structure that I'm going to analyze will be this beam AD. And we also mentioned earlier when we have a pulley, we want to analyze the pulley separately as well. So as that being said, we can demember the entire structure into three components. One is this beam AB, and one is this two-force member BC, and one is this pulley. And we're looking for reactions at A and the C. So let's just do a quick sketch on this given diagram and to draw the reactions on this member AD. So after I set up the XY coordinates, I know at pin A there are two reactions because this is a fixed pin support. So two reactions, one is along the X direction, one is along the Y direction. So I'll call that AX and AY, both pointing to the positive direction we set up. And at pin B, since there is member BC is a two-force member, so the force exerted at pin B must be along the direction of this BC member. So this, I will call it FBC. And so far, those three values are what we are looking for, AX, AY, and FBC, because we're only looking for the force at C. We're not looking for the component of force at C. But don't forget, we also have a pin at point D connecting the member AD and the pulley D. So, but overall, that's just a pin connection. So, or pin support. So there will be two support reactions as well. And see, my dear, well, just again, this is just the beginning initial analysis I usually do before I start to draw my other my facial free body diagrams. Just want to see if I have enough information to solve what I need to. So again, just ignore the BC, the wall, and the pulley. Just think about this member AD. There are a total of 5 unknowns, but we can only write 3 equilibrium equations. So that means we need to eliminate, or we need to find another free body diagram to figure out at least 2 unknowns. And that will go to this free body diagram of the pulley. Since the force dy and dx are the reactions between the action reactions between this member AD and the pulley D at D. So if we can draw the free body diagram of the pulley and solve for dx and dy, then we move to the member AD, then we will have enough equation to solve the leftover unknown values. Okay, so that's kind of the strategy. So let's now start our real solution to first draw the free body diagrams of each component. So the first free body diagram includes the pulley, actually, and also the cylinder is part of this system as well. So I included the pulley in the cylinder and also a portion of the cord. So it's kind of like you section the cord from here and you take the pin off at D. So that will be the system. So this pulley will be off the AD member, and we'll take this as a whole system to draw the free body diagram. So again, not only the pulley, but part of the cord and the cylinder as well. So in this free body diagram, first at the pin center D, we have 2 reactions because that's a fixed pin. So we have an X reaction, a Y reaction, dx and dy. And then is the cord. So cord can only exert tension, and since this is the one continuous cord, so the force developed within the cord is the same anywhere, and it should be equal to the weight of this cylinder. So the 50 kilonewton, it's not kilonewton, sorry, the 50 is kilogram, so we need to use it to calculate for the weight of the cylinder. And now this is a complete free body diagram of the system, including the pulley. And next, we're going to write equations of equilibrium. And we just mentioned for pulley, there are only 2 equilibrium equations. One is the x, sum of fx equals to 0, and another one is sum of the fy equals to 0. For the first equation, we will have dx, which is in the positive x direction, minus t, which is equivalent to this weight of the cylinder, equals to 0. So those are the only 2 forces in the x direction. So we can solve for dx, which is 490.5 Newton. And same idea for the y direction force. We have dy minus the same value here equals to 0. So dy has the same magnitude as d of x. Next, let's draw the free body diagram of this member AD. Since we said the member BC is the 2-force member, and the 2-force member is just used to simplify the problem, we don't need to draw the free body diagram of this 2-force member BC. But we do know if this is the 2-force member, then the reaction at pin B must be in the direction of BC. So we just need to place one reaction at pin B. We call it FBC. That's again something we are looking for. And at pin A, there are 2 support reactions are unknown, and those are the 2 values we are looking for. So we call it A of x and A of y. Now, at pin D, we know pin D connecting the member AD and the pulley. So at pin D, those reactions supports are action and reactions. So we're going to use dx we solved earlier from the pulley. So on the pulley, we assume dx is in the positive x direction. So on this member AD, its reaction will be in the opposite direction, but has the same magnitude. So I'm just going to draw this in the x direction, but it's the negative x direction, and I'm going to write down the value directly. Here, dx is 490.5 Newton. We solved from last step. So again, that's the reaction of the force on this pulley at point D. Same idea in the y direction is also a reaction of the pulley. So on the pulley is pointing to the positive direction, y direction. So on this member AD will be pointing down. So this will be dy. That's the same force again, just in an opposite direction. And double check your free body diagram to see if did we miss any applied forces or support reactions. Pin A, we have two reactions. At pin B, that's the two force member, so there's only one reaction along the two force member. And then at pin D, there are two reactions, which are the reaction of the pin D acting on this pulley. Okay, so we have everything. And now you can check the number of unknowns. We have three unknowns, AX, AY, and FBC, which are the values we're looking for. And we have three equations. Therefore, we can solve all of them. So write down the equilibrium equations. So the first equation we're going to use will be the moment about point A is 0, since it has the most number of unknown values. So with that one, there's something else we missed for the free body diagram, is the geometry. Okay, so I just put the distance between those points on the free body diagram, so we can start write the equilibrium equations. So first we will have FBC, which will have a positive moment because it's counterclockwise rotation. The moment arm is 0.6 meter, and for the component dy, it's pointing downwards, so it will be a negative 490.5, and the moment arm is 1.2 meter, and for the dx is a positive moment, and the moment arm is 0.9 meter, and this should be 0. And in this equation, we just have one unknown, which is FBC. So solve FBC. FBC equals to 245.25 Newton. And next equation I'm going to use will be the sum of Fy equal to 0, because in that direction we only have one unknown, which is the Ay. So Ay minus dy, which is 490.5, is 0. So Ay will have the same magnitude as dx and dy. The last equation will be sum of Fx equals 0. So we have Ax minus FBC, since we already solved FBC, so we just plug in the number here directly. And then minus d of x, 490.5 equals to 0. So we solve Ax to be 736 Newton. And now this problem is solved. Now in this example, the structure is even more complicated. We have a couple of pulleys and we have different different beams. So let's see. We have this given structure and the external load here is 700 pound force. The force in the cable at this motor W and horizontal and vertical component of pin reactions at A, B, C, and D are to be found. In other words, we are looking for all the support reactions in this given structure. So our plan will be, we're going to draw the free body diagrams of the frame's members and the pulleys. So again, if we have pulley, then usually we are going to draw the free body diagram of the pulley and try to solve some reactions at the pin in the center of the pulley. And then apply the equations of equilibrium and solve for the unknowns we're looking for. Now, take a look at this entire structure. There is only one given force, which is the 700 pound force applied directly on this pulley E. So we'll start from the free body diagram of this pulley E, because you want to use this given information and start from the structure directly related to this given information. Therefore, we're going to draw the free body diagram of the pulley E. So it will just be a circle, and the 700 pound force is applied at the center of this pulley. And then we have the two cables pull on both sides of this pulley. And since I said it's one there are two cables, but actually that's just one continuous cable or string in this entire structure. Therefore, the force developed within this cable is the same anywhere. So we'll say that's the tension T developed in this cable. And this will complete the free body diagram of the pulley E. Okay, so we then can solve for the tension in the cord, and we didn't set up the X and Y earlier, but let's write down the XY coordinates as 0. And there's only one equilibrium equation from this free body diagram, since all the forces are pointing in the Y direction. And we can solve T is half of this 700 pound force, which will be 350 pound. So after we figure out the tension in those cables, we're going to move to this pulley at C. So first the outline shape of this pulley C, and then on this C we have the cable pulled. One is pulling down and one is pulling from the right to the left, and again that's the same cable we just analyzed earlier. So we know, right, the force developed in this cable is 350 pound force, so that's the given value now. And next, at pin C, in the middle of this pulley, that's a pin connection. Imagine we're going to take the pin off away from this pulley, but we need to leave the support reactions at this location C. So for a pin connection, there are two supports, which one is in the X direction, we call it CX, and one is in the Y direction, we call it CY. So at this point, you may argue what happens to this string or cable pulled down connecting to this pin at C. Well, imagine when we take the pin off at C, we take the string or the cable off at C as well. So as a result, we only leave two reactions at point C, CX and CY. And we're going to consider this tension exerted by this cable when we analyze the member ABC later. So again, if we're going to draw the free body diagram of the pulley C first, we don't have to consider the cable exerted at C. We just need to use two support reactions at the pin C. And now this is everything for the free body diagram of this pulley C. Then clearly we can write two equilibrium equations. One is in the x direction. We can solve for Cx from this equation, and one is in the y direction, and we can solve for Cy from this equation. Next, let's do the free body diagram of the pulley B. So first, pulley B also has the tension exerted by the same cable. One is in the direction of BC, one is in the direction of, there is a 60-degree angle with the horizontal direction, so we can say there's a 30-degree angle between this force and the vertical direction. And next, we need to place the pin reaction at the center of this pulley B. Same idea as the pulley C. So there will be two reactions. One is Bx, one is By. So those are everything we have for this pulley B. Two reactions by this cable and two reactions by the pin. So we can write two equilibrium equations to solve for the two unknowns, Bx and By. So Bx can be solved from the sum of Fx equals to 0. So be very careful with the numbers you use in the free body equilibrium equations. Since in the free body diagram we indicate Bx is pointing to the left, but in the we indicate that right. Pointing to the right is the positive direction, therefore it must be a negative Bx. And the same idea for the x component of this 350 pound force exerted from this motor to this pin B. And the By can be solved from the sum of y equals to 0. Next, let's draw the free body diagram of member ABC to solve for the support reactions at pin A and also at pin D. So please note member BD is a two-force member. This is the beam ABC and the dimension of the beam. And then at pin C, since we already figured out the reactions at pin C on this pulley C, and those are action and reactions. So on pin C, there is a force in the positive x direction or pointing to the right. Therefore, on the member ABC, the same location, there will be a reaction of the force which will be pointing to the left with the same magnitude, 350. And in the y direction, the force is 350 pointing up, therefore on this member ABC will pointing down. But here, instead of 350, it's 700. The reason for that is because we said at pin C, not only the pin is connected here, or not only the pin exerts a force in the y direction, but also the cable here. And we know the cable exerted a 350 pound force. So 350 plus 350 exerted by this pin C. So the total value will be 700 pound force exerted at point C on this member ABC. And next, at location B, at pin B, the forces are the reactions of this pin B exerted on this pulley B. So there will be a 175 pound force pointing to the right along the x direction, and along the y direction there will be a 303.1 pointing down, which is the reaction of this y force on the pulley B. And also at point B we have this two force member BD, and we need to look for the reaction for this force, for this member BD. Since it's a two-force member, so we'll assume there is tension applied at pin B on this member ABC. So it will be along the direction of this BD member, and TBD is what we call it. At pin A, we haven't solved for anything at A yet, so we'll just say that at the fixed pin support, there will be two reactions. One is along the X direction, and one is along the Y direction. And this is everything for this free body diagram of the member ABC. So be very careful with point B and point C. So at point C, in addition to the pin reactions, X and Y reactions, there's also the cable pulled at C. At B, in addition to the pin reactions BX and BY, we also have this two-force member pulls away from B. But again, this pulling force is our assumption. It might be a compression. We need to solve to see the direction or compression or tension of this member BD. And if we check the number of unknowns in this free body diagram, we have AX, AY, and TBD, a total of 3 unknowns. So we can write 3 equilibrium equations based on this free body diagram to solve all of them. With moment about point A, we can solve the TBD, which is 2,409 pound force, which means it is tension. And with Fx equals to 0, we can solve for Ax, and with Fy equals to 0, we can solve for Ay. We can also take one more further step to figure out the component of the reactions at pin D. In other words, we can find a dx and dy, not only the resultant force along the BD direction. So to do that, we need to draw the free body diagram of the member BD. And BD makes a 45-degree angle with the horizontal direction. And we already solved for TBD, which is in tension. So we'll pull this away from this member BD, and at point D, we want to look for the two support reactions. So one we say is a dx, one is dy. So this will finalize the free body diagram of this member BD. So we just need to write 2 equilibrium equations to solve for dx and dy. So one equation is the sum of fx equals to 0, and one is sum of fy equal to 0. Or we can just say the dx equals to the negative x component of TBD, and dy equals to the y component of TBD. And now this problem is solved.